Hello everyone. In this session, we're going to compare low end and high end shaver, and also we do the comparison of two types of cellular phones. In this section, we study practical examples of battery management system implemented in real portable products. First example is shaver, where we compare low end and high end model. This comparison helps us understand how product cost and features influence the complexity of the BMS. The second example is cellular phone. Here we compare two types of phones. Type A supports only nickel metal hydride batteries, while type B supports both nickel metal hydride and lithium ion batteries. This example shows how changing battery chemistry increases BMS complexity and requires architectural redesign. Though these examples, we can clearly see how cost, product features, battery type, and performance requirements directly affects BMS design. In this low-end shower BMS, cost is the most important factor. It uses nickel cadmium and nickel metal hydride batteries integrated inside the shaver. Here we are going to use nickel cadmium or nickel metal hydride battery. The power module is also integrated inside the device. Both energy conversion control and charging control functions are implemented inside a high voltage IC. Full battery detection is done using temperature measurement. Two NTC measures the battery temperature and ambient temperature. When the temperature difference reaches a certain level, the system detects the battery is fully charged and switches to trickle charging. Okay, there is no battery status indication for the user. This keeps the system simple and cost effective. Now let us look at this high-end shaver. Here two batteries are connected in series. A microcontroller is also added, which significantly increases the intelligence of the system, where the system performs Coulomb counting, meaning it measures the current flowing into and out of the battery and keeps tracks of the state of the charge. It also compensates for self-discharge based on the temperature. Okay, the user receives the battery information through an LCD display, such as minutes left or saves lefts. Thus, compared to the low-end model, the high-end shaver has more features, better battery monitoring, and higher BMS complexity. Now, coming to cellular phone type A, which uses NiMH only. In a type A cellular phone, only nickel metal hydride battery packs are supported. The battery pack contains 4 NiMH cells in series, giving a total voltage of 4.8 volt. The power module only performs energy conversion control. The entire charging control function is implemented inside the phone. When a battery pack is connected, the phone reads the identification register to determine the battery type and capacity. Okay, where the charging is performed at the fixed current of 800 milliamps. And full battery detection is achieved by analyzing the voltage and temperature derivatives, which is typically for NiMH batteries. Now, after the full detection, the system switches to trickle charging to maintain the battery at full capacity. In terms of power supply, the power amplifier operates directly from the battery because the battery voltage is high enough. Since the battery has low internal resistance, a small buffer capacitor of around 100 microfarad is sufficient. Okay, now coming to cellular phone B, which supports nickel metal hydride as well as lithium ion battery packs. Okay, where Type B is a more advanced and compact phone. It supports both NiMH and lithium ion battery packs. The standard battery is a 3.6 volt lithium ion cell with an integrated electronic safety switch. Okay, an optional NiMH battery pack can also be used in this. Supporting two battery chemistry significantly increases BMS complexity because each chemistry requires a different charging algorithm. Now, for lithium ion batteries, charging is done using constant current followed by a constant voltage at 4.41 volts. Okay, temperature is used only as a safety protection parameter in lithium ion batteries. And for NiMH batteries, charging still relies on voltage and temperature slope detection. In this design, the PWM switch is moved to the power module to reduce the heat inside the phone because the battery voltage is lower at 3.6 volts. A DC boost converter is required to step up the voltage to 4.8 volts for the power amplifier. Here we are going to use a DC-DC converter for the boosting 3.6 to 4.8 volt. Okay, now what are the key difference between type A and type B, or I can say phone A and phone B. The main difference between phone A and phone B lies in the battery chemistry and voltage level first. Next, phone B operates at a lower battery voltage of 3.6 volt. It also includes safety switches and additional protection components for lithium ion batteries, which increase series resistance. Due to the lower voltage and higher resistance, the power amplifier cannot draw peak current directly from the battery. Therefore, a much larger buffer capacitor, approximately 2 millifarad, is required. Additionally, a DC-DC boost converter is needed to increase the voltage for the RF circuits. This example clearly demonstrates that changing the battery chemistry does not only affect the charging algorithm but can require a complete redesign of the BMS architecture and power supply system. Okay, these real product examples shows that the battery management system design is strongly influenced by product cost, required features, battery chemistry, and performance demands. As the product becomes more advanced, the BMS becomes more intelligent and complex. Thank you.